Hello, everyone. Welcome to the IEEE Computational Intelligence Society Santa Clara Valley chapter sponsored event. There are a host of other events, host of other chapters and organizational units who are co-hosting this event. So on behalf of all the hosting organizational units of IEEE, I welcome you all. So we'll first start with the presentation by a Google senior software engineer, Sujitra. So you want to come to the podium and introduce yourself? So you can put it here. Yeah, you can use
Hi,
it. You are sharing it? You are sharing.
yeah. So how do I?
Are you in the meeting or not yet?
How I should join the meeting?
Yeah.
Okay, one second.
Or we can do one thing. Just a few minutes, we are trying to set up here. Do you have the meeting ID? Sign to join. Oh, you have to sign in.
These tables are in interesting directions.
This meeting is being recorded.
Okay, good. So it looks like it's going. So it looks like it's going to take time for the first speaker to set up her presentation. So we will go with the next presentation, which is by Mayank Kapadia. He is a student of Applied Data Intelligence in the Department of Applied Data Science at San Jose State University. And he has been working on this demo in Embodied AI. So I'll hand it over to Mayank. And he's also my research assistant and instructional student assistant as well. And the good thing is he is a prospective PhD candidate. So welcome, Mayank.
Thank you, Professor, for such a great introduction. So, as discussed today, first of all, I will introduce myself. Myself, Mayank. I am working as a research assistant under Professor Vishnu, and we are working on an embodied AI course. And today, I am going to show a demo regarding the same. So today we are going to answer a simple question: Can we teach a robot to think, not just following instruction, but genuinely learn, adapt, and figure things out on its own? Over the next few minutes, we are going to go through three approaches we tried, what worked, what didn't, and what we learned from each one of them. And along the way, I'm going to show you the demo, as you will see the robot actually running, not just slide about it. So let's start with the most obvious approach. The first approach where we script the robot. So we built a virtual warehouse in Isaac Sim and wrote a script that tells the robot exactly where to move, how to
Manic, Manic,
and where to place the object.
Manic, your self show video is obstructing your slides, and you have a banner at the bottom of your screen. The blue right next to the blue button is the hide button. Click that button. Perfect.
Okay.
But your self video is still hiding your slides. Thank you.
Thank you for that. So this is the scripted demo where place of an object is fixed. The robot arm will move exactly where the object is present and it will try to pick the object. So this is how the normal scripted one work. So as you can see clearly that it's able to pick the object. So from this, we can easily notice that it works perfectly fine every single time without any hesitation, never fail, never sound second guess itself. This look impressive. And this type of learning, it's obviously we call it as impressive engineering. So here is a catch. So what if I do a little change in a code? Let's say if I change the box coordinates from point 0.4 to point 0.5, that is, I just moved it, let's say 5 centimeter, that is 0.45. And when I run the same code, it's the same robot, same script, same warehouse. I'll just make a small change, and as you can see, it fails. So So this is the fundamental problem with the scripted robot. They don't see the world, they just remember the path. So what just happened? The demo reveals something deep about the traditional programming. A scripted robot knows exactly one path. Change the position, the lighting, or anything, and it fails completely. Zero adaptability. What we actually want is a robot that adapts the way a person do. You walk into a room, the chair is in the wrong spot, you go around it, you don't crash into it because your mental map says the chair should be there. The gap between what we build and what we actually need is the entire motivation for everything that follows. So let's consider a scenario. Think about how you learn to catch a ball. Nobody programmed your joints. You tried, you missed, you tried again. And your brain give you a tiny reward signal every time you get closer. That dopamine hit said, yes, move, we can do one more time. Over hundred of attempts, you will build intuition. You stop thinking about where your hand should be and just caught it. That process, trial, fail, reward, repetition, is exactly what reinforcement learning does. And that's the second approach we tried. Before going into the demo part about the reinforcement learning, we need to understand the goal, how it looks like, how we train the robot. So we design a reward system, which is about 500 lines of code that tells the robot what goods look like. So we divided the whole reward function into three phases. First phase, get closure. So in that particular robot tries to move towards the box, we will give them points for that part. In second phase, it tries to pick it up. Successfully gripping the box, more points. Now it's learning dexterity. Now the final part is to carry to the target, deliver the box to the goal. This is called reward engineering. And the art of translating human intent into a robot can be optimized. So now we are going to look at the reinforcement learning script, and with the use of GUI, I will show you some pros and cons of it. So the pros is that you can see how robot is training each robot. So right now there are four robots learning simultaneously. You will observe that one robot helps other to learn something better. But the catch over here is when you see how much time it will take, it's showing 125 hours. That is out of scope because of lot of time. So the best option is to train using headless function. So the main difference between headless and head is with GUI and without GUI. Now just observe the time it will take. Now as you see, the time decreased to 1 hour and 36 minutes. So here what it get interesting, we don't train one robot, we train 256 simultaneously. Every robot tries something slightly different. A tiny variation in angle, speed, or grip pressure. The number of screen tells the story. 256 parallel robots. 256 parallel robots across the environment and over 30 million total training steps. With six environments running visually like this, it takes more than 120 hours. Just changing it to headless, it drops to directly 1 hour. That's the power of parallelization. So I did train the model beforehand. I will show you the directly the result, how it looks. So as on your left, you can see there are various runs. So few of them are the trials. You can understand by the timestamps it shows. So the best one which I ran was this one. So let's focus on two specific diagrams. So first one is about episode length mean. So as you can see from the graph that robots went from zero learning reward to 7,700 learning reward. So that tells a story that with increasing timestamp, the robot is learning something. And let's understand this approach with another diagram that you can get from your training data, that is your explained variance. The explained variance tells the story that the part of network that predicts the future reward. It's also improving. When it was started with zero, policy has no reliable signals to learn from. As it rises, training stabilizes. But you notice something that we trained it for 30 millions. Reward went from 0 to 7,700. Lifting success rate we got was 35%. Near target rate we got was 56%. But the overall success end to end we got just 4%. The robot learns to reach and left, but precise placement it's still a research problem. That's why. So until now we understood two different approaches, and with them we have two different limitations. Scripted controls is rigid, 5 centimeter change breaks everything. Reinforcement learning is powerful but demands millions of attempts and still only get 4% of success. So this raises a real natural question. Can we do something better? Think about how you train a new employee. You don't hand them over directly the 500-page manual. You show them, they do it once, they try. That's the intuition behind imitation learning. So, what is imitation learning? Imitation learning flips the paradigm. Instead of programming the robot, we explore randomly for millions of steps. We directly show it how to do the task. The robot records everything about the demonstration, the position of arm, the object location, every action taken, and it then train a neural network to replicate that behavior. This specific technique is known as behavior cloning. We are tuning a reinforcement learning problem into a supervised learning problem, and supervised learning is far more efficient and easy to understand than reinforcement learning. Now, uh, to train a model, we require a data. So we tried two different sources to get the data. One source is human teleoperation. The second one is the scripted automation. So in scripted automation, we tried various 50 different cube position, systematically varying x and y coordinates. Every single one succeed if it's planned, deterministic, and perfectly clean. This teaches the model what correct behavior look like across a wide range. So this is how the scripted will look like. So every single run will be succeed because it is planned, deterministic, and perfectly clean. This teaches the model what correct behavior looks like across a wide range. But it has a blind spot because everything is pre-planned. The robot never see a near miss, never has to recover, never handles an awkward approached angle. It only knows the perfect part. So this builds on the second approach that we use to collect the data, that is human teleoperation. So what does human teleoperation means? So we developed a custom keyboard interface allowing direct control of the Franca arm in real time. We use WASD for the movement, QNE for the vertical adjustment, and K to operate the gripper. We manually demonstrated the pick and place maneuvers. So I will show you how I can control this Franca. So with the help of WASD, I am moving the Franca arm forward, backward, on the left and on the right. With Q, I am moving the Franca arm below. So this is the way I control the whole Franca arm. But this is where it took me roughly 20 minutes to record just the 10 demonstration. As you can see, it was little time complex. So, but this data is irreplaceable because it teaches recovery. How I am not following a fixed path, I am adjusting correctly, trying slightly different angle. That exactly what the scripted data can never provide. So these two data sets are not interchangeable and we don't treat them equally. We weigh them differently by design. The scripted data set gives us the scale and consistency, 50 clean demonstration, perfect trajectory, no noise, but it assumes the robot always know exactly where the cube is. So training only on this and you get the robot that memorizes a script. Sound familiar? The human data set, which we created, the 10 demonstration, is small, but for reacher. During teleoperation, I introduced subtle correction, varied approach, and recovery from misscript. Those imperfections are actually the signals. They teach the robot how to handle the unexpected. So, our training strategy assigns higher weight to the human demonstration because they teach failure, recovery, the things that actually determines the real world success. The scripted data provides the backbone, the human data provides the resilience. I wanted to be completely transparent about where we are. We have built the full pipeline, teleoperation interface, scripted collection, combined weighted training strategy. Everything works, but we haven't able to fully validate the training policy yet. The reason is simple. We don't have enough data. With only 10 human demonstration, the model overfits immediately. The training loss drop beautifully, but the validation loss goes in opposite direction. This is the best scenario of overfitting. The important distinction, the pipeline is working correctly. The model trains, the motion is smooth, The arm moves purposely. The bottleneck is the scale of high quality human data. And that's our very next step. So let me bring it all together. We have built three approaches. Scripted control shows us that perfection without adaptability is fragile. 5 centimeter broke everything. Reinforcement shows us that the learning from scratch is powerful and brutally expensive. 30 million attempts, 125 hours of training, 4% success. Imitation learning showed us that the human knowledge, even imperfect human knowledge, is incredibly valuable. The motion becomes smooth, even with just 10 demos. Each approach taught us something that previous one couldn't. That's not the failure, that's what research looks like. The robot is still learning, so are we, and that's exactly what makes the worth doing. Thank you for your time and happy to take the questions.
Questions in the Zoom window either. So, yeah, thanks, man. That was hopefully useful. So we'll move on to the next speaker. Uh, so you're able to share your screen? So we have 68 registrations actually, but quite a few of them are online and some of them are on YouTube.
Hi, good evening, everyone. So, good evening, everyone. My name is Sujitra. So, I'm a software engineer working on cloud AI infrastructure.
Yeah, go ahead, please. I'm just trying to use this.
Okay. So, today we are going to talk about the most expensive and complex machines we have ever built, the AI hypercomputers. So, most people look at AI and then see it as a software revolution. But for the next 30 minutes, we are going to look under the hood. Like, we aren't here to talk about how training algorithms work or the complex math behind it. We are going to look the fabric that makes these LLM trainings possible. Okay. So we have all seen this chatbot UI. So it's very clean, simple, and it feels like magic. But actually, on the back end, we have a massively parallel distributed computing fabric. So why can't we just run an LLM on one really big computer? Because we'll hit the memory wall. So even when we are using NVIDIA's H200 GPU, so H200 is basically NVIDIA's tensor chip. So that's an enterprise AI grade chip. So even with NVIDIA H200, which has about 140 gigabytes of RAM, we can hold only a fraction of frontier models parameters. So to train these models, we have to shard the model across thousands of nodes. So inside, if you look at H200, like inside H200, there is a high bandwidth memory bus, and then the data moves at 4.8 terabytes per second. So when we need to sync model results across nodes over a traditional network, we are dropping from terabytes per second to gigabits per second. So this is where the birth of AI computer came in. So here we are not just networking servers together anymore. We are trying to make thousands of GPUs act like a one single massive processor. So in this environment, the network isn't just a peripheral, it's the system's backplane. So because AI training is very much synchronous, so this thousands of GPU cluster moves only as fast as the slowest packet. So even as one straggler packet can effectively stall the entire GPU cluster. So these clusters cost thousands of hundreds of $1 million to build and to power them. If your network stack is inefficient and if you're losing performance to standard TCP, overhead or unnecessary data copies, we are essentially losing the money. So we have to move away from best effort network to build a guaranteed performance fabric. Okay, so we all agree that we need to build a AI hypercomputer. So what does that actually look like architecturally? So to make this fabric work, we have to optimize for three specific pillars. First is high throughput. So during an, I'm sure everybody might be aware of the collective communications library. So during an all reduced step, we aren't just sending few packets. We are sending hundreds of gigabytes of gradient data across the fabric simultaneously. So the network must be able to handle such huge burst of simultaneous data without choking. So the second pillar is ultra low latency. We are talking about microsecond level requirements. So in NLM training, every nanosecond that is spent in the network stack is a nanosecond the GPU isn't doing any math. The third and the most important one is the jitter-free delivery. So in a synchronous system, like average latency is not that useful metric. So what matters is tail latency. I'm sure you might have heard what tail latency is. So tail latency is the time taken by the slowest packet. So if 99% of GPUs are ready, but if one slow packet is delayed by a jitter spike, the entire GPU cluster stalls. So we need a fabric that is predictable and it is inconsistent. So how do we build that fabric? So we tackle this in two physical layers. So inside the chassis, we have scale up using NVLink. So NVLink is NVIDIA's technology for connecting GPUs within a single server. So it provides a massive bandwidth, but it is physically limited to a box. To reach 1000 plus GPU cluster scale, we have to definitely scale out. So this is where SmartNICs and RDMA will come into picture and they help extend that performance across the data center. So the challenge here is to make the scale out network feel as seamless and fast as the scale up NVLink network. So the mental model I want you to have for the rest of the talk is the network is no longer a simple IO device. It is the memory bus. So just as your CPU talks to RAM over local bus, these GPUs in a big cluster, they must talk to the global memory of the cluster over the network fabric. So this is what technologies like RDMA have been moved from the niche world of supercomputing into the data center. So we are turning the network into a remote PCIe bus. So I'm sure you might have know what is PCIe bus. Uh, okay. So now we want the network to act as a memory bus. So for that, we have to look how we have been doing networking over the last 40 years. So we all aware of TCP and we have been using TCP IP. So it's the bedrock of internet. Like it's extremely reliable, resilient and flexible. But for microsecond level synchronized AI training, this flexibility is not of that great help. So think about what happens when a packet arrives via TCP IPs. So in a traditional stack, the CPU is the middleman. So when the NIC receives the packet, it puts in the kernel buffer, and the CPU then must manually copy the packet to the application's memory. And in case of AI training, so this ML library that is running in the user space have to copy the data from the application memory to the GPU memory. So imagine at 400 gigabits per second, this copy is a massive tax. It consumes a lot of CPU cycles. It eats up system memory bandwidth. So in AI computer, we cannot afford a middleman. So we have to do complete zero copy networking, where the data from the wire directly goes into the GPU memory. without the CPU ever touching it. So we are not just moving the data, like it's not just the copy that is the overhead. Like at high bandwidth speeds, the number of interrupts, like whenever NIC receives a packet, it puts the packet in the kernel memory buffer, and then it triggers and fires an interrupt. So whenever an interrupt is fired, CPU has to do stop whatever it is doing and then come to handle that packet. So it involves a context switch. So at a high bandwidth, like this interrupt storm is very high. So we are no longer limited by the speed of the network, but we are limited by the operating system overhead. So TCP was mainly designed for uh, internet, like it uses mechanisms like slow start and congestion window to find the available speed. But in AI cluster, we have a locally very controlled network. So we don't want a best effort functionality of TCP/IP. We need a deterministic and wire speed delivery. So to get that, we have to bypass the kernel entirely. Okay. So now how do we take the CPU out of the work? So we have to move the work that kernel is doing into the edge of the system. That is, we have to move the functionality into the NIC. So that's where the birth of SmartNIC. So as the name implies, SmartNIC isn't just a faster network interface. It's a dedicated network engine. It takes the transport completely. It takes the transport layer of the kernel and it's offloaded into the hardware. Like typically, we used to run the TCP/IP stack in the kernel, but now the transport is running on the NIC. So when a packet arrives, the smart NIC handles the headers, checksum, and it handles retransmissions, ACKs, and everything in the hardware. The CPU is never interrupted. Uh, so with so what is RD? So SmartNIC are the ones that enable RDMA. So what is RDMA? RDMA is a remote direct memory access. So when we say RDMA, we typically mean that NIC is directly able to access the system RAM without CPU's involvement. When we say GPU direct, it means that NIC is able to directly access the GPU's memory without the host CPU's involvement. So with GPU direct, we use peer-to-peer direct memory access so that the smart NIC and the GPU can talk to each other over the PCIe bus. So we completely skip the system RAM and CPU entirely. So in this new world, so in the previous slide we saw when a packet comes, when we want to transfer a incoming packet to GPU memory, first the NIC will write the packet to the kernel buffer, and then CPU will copy it to the user space ML libraries applications memory buffer, and from there the data is copied to the GPU. But with the GPU direct, there is no system RAM and CPU involved. NIC directly places the packet in the GPU's memory. So that is GPU direct. So when we are synchronizing millions of weights across thousands of GPUs, these invisible copies add to a lot of microseconds of delay. So by using GPU direct or RDMA, we ensure that network is not a slow, and it acts like a high-speed memory bus. Okay, so we talked about SmartNIC. So we also will look into RDMA. So RDMA is the protocol that treats the entire cluster like a one giant pool of memory. So RDMA, as the remote direct memory access protocol, it's a very old technology. It's not something new, but with the advent of AI, this has been widely used now. So in the world of RDMA, we have two ways of moving data. So two-sided communication, where both the sender and the receiver are active. So this is mainly used to establish the control path or the control signal. So it runs a handshake protocol, which is required for the data transfer that will happen next. So the real power of AI is one-sided communication. That's RDMA read or write. So once the handshake is done via the two-sided message, the sender gets a key to the receiver's memory. From that point on, it can write data directly to the remote GPU's memory without the receiver's CPU getting involved at all. So this is how the RDMA works. Like you get a, so basically first sender and receiver will exchange a key for their memory. And once the sender gets the receiver's key, it can use that key and then directly write data to the receiver's GPU memory, bypassing the receiver's OS and host CPU entirely. But one might wonder, like, what about if you allow NIC to directly access the memory? What about the security? RDMA has a concept called memory registration. So before allowing NIC to read or write data to the memory, so the applications generally they pin the memory, so telling the OS that this memory is for DMA, so don't move its physical pages. And then the application hands a security token to the NIC. So this ensures that NIC can only touch the specific buffer we have authorized. So this enforces access, restricted access, and also it provides high speed. Because we completely removed the host CPU from data handling, we dropped our latency from double-digit microseconds to sub-nanoseconds. When we are performing millions of these all-reduce operations across a LLM training job, this 10x or 20x reduction in latency difference is what allows the cluster to scale linearly. Okay, so we moved the transport to the hardware with the SmartNIC. So now we are going to use a very standard Ethernet network. So in standard Ethernet, packet loss is unavoidable. So in a traditional networking, packet loss is handled by TCP. So TCP has the sliding window and retransmission logic. But when this transport is running on the hardware, the silicon, when a single packet is dropped, it triggers a go back and retransmission at the hardware level. So hardware is basically optimized for speed. It's not optimized for complex logic. So in TCP, when, for example, if a sender sends packet 1, 2, 3, 4, 5, and if packet 2 is lost in the network, TCP has a selective retransmission where it can retransmit only the lost packet 2. But in case of if the transport is implemented in hardware, and if packet 2 gets lost, hardware implements a go back and retransmission. So in that case, the hardware has to retransmit 2 to 5, all the packets starting from 2. So packet loss is costly, and because RDMA is designed for high performance and low latency network, it assumes a lossless fabric. So we cannot rely on best effort delivery. So we have to make sure that the fabric is lossless. So Ethernet is a standard commodity fabric. So how can we make Ethernet lossless? So in a typical Ethernet network, the switches, like when their buffer is full, they are configured to drop the packet. But to make the Ethernet lossless, we implement priority flow control. So what is priority flow control? Priority flow control is something when a switch, like when the switch buffer reaches a particular occupancy threshold, the switch will alert the sender NIC to, it will send a pass frame asking the sender to buffer the packet and not send any more packets. So it's a reactive measure. So the switch will not wait for its buffer to overfull and then drop the packet. So when it reaches some 80% on some threshold, it will immediately send a pass frame. So by that way, the sender can slow down on it creates a back pressure to the sender. And another technique is explicit congestion notification. So the switch marks the packet, like when the switches in the network, if they sense congestion, they add it, they signal it in the packet. So when the receiver receives the packet, if there is any congestion notification, it just relays back to the sender in the acknowledgement packet. So by that way, the sender can slow down the ingestion rate and everything. So the priority for flow control and explicit congestion notification is what transforms the standard Ethernet network into a deterministic fabric. So why this lossless is non-negotiable for AI? Because it comes down to the synchronous barrier. In a training step involving thousands of GPUs, the entire cluster must wait for the slowest packet to arrive before the next compute cycle can begin. So a single retransmission, we saw that like if a single packet is dropped, the hardware has to go back in and then retransmit everything from that. So a single retransmission can create a massive spike in tail latency. If the 99 percentile latency is order of magnitude higher than the average, the model flop utilization will collapse. So in the AI hypercomputer, we are not optimizing the average latency of the packet. We are architecting to eliminate the outlier packet. So optimizing for tail latency is very, very critical. So that must be minimum, the tail latency. Okay. So we now saw we have the SmartNIC and we also have the lossless network in place. So now the architecture challenge is physical. Like how do we interconnect these thousands of GPUs without creating a massive bottleneck in the network? So the industry solution is a special cabling pattern called rail optimization. So in a standard server, in a standard 8 GPU server, each GPU has its own dedicated SmartNIC. So in a rail optimized design, we don't connect all these 8 SmartNICs to the same top of the rack switch. Instead, we create 8 independent parallel fabrics. That is GPU 0 of every node or every server in the data center is connected to a independent dedicated leaf and spine switches. So this means during collective communication operations like all reduce, where every GPU needs to synchronize the gradients, this massive burst of traffic stays within its own dedicated lane. So because the traffic is sharded by GPU index, we significantly reduce the complexity of congestion management. So ML communication libraries like NCCL, NVIDIA Collective Communication Library. So they are aware of this rail optimized topology. And when they are forming the communication ring, they make sure that GPUs 0 of all servers and GPU 1 of all servers only communicate to each other. So isolating traffic into rails prevents contention and also bottleneck that can occur when the network is a shared fabric. So this rail optimized topology ensures that the tail latency remains low so that the cluster spends its time in compute phase rather than in the stall phase. Okay, so now we looked at the individually the H200 GPU, SmartNICs, and RDMA protocols. So the ultimate question is how efficient is this AI hypercomputer? In the AI world, we measure this using MFU, model flop utilization, like flop is floating point operations per second. So theoretically, a cluster of 10K H200s has a very good performance. But however, when we connect them using a traditional TCP-based network, we get only 20 to 30% of the MFU, model flop utilization. This means 70% of the investment is sitting idle, waiting for the network to catch up. So by implementing kernel bypass, SmartNIC and RDMA and the rail optimized topology we have discussed, so this utilization improves to 60 to 70%. So we are effectively doubling the work that a GPU cluster is doing without adding even extra GPU. So in the recent times, the bottleneck for training next generation of models is no longer the speed of the silicon, it's actually the interconnect bandwidth. So to wrap up, we have moved past the era of where servers servers are connected by a network. We have entered the era of AI hypercomputer. So in this new paradigm, the network is not a peripheral, it's a system backbone. So by treating the entire data center as a single memory coherent fabric, we enable this intelligence to be possible. So the goal is simple: ensure that train to time is limited only by the speed of light and not by the overhead of operating system. Okay, so references, so the numbers and the throughput numbers and the latency numbers in the presentation are taken from the NVIDIA spec. So it has been listed here. Yeah, that's all for the talk today. Any questions?
Question from online?
So yeah, so this problem can still be there at edge also. So now do you, but this kind of infrastructure may not be available at edge. So do you see there is a network, more innovative things come in the network that can make these things to solve at edge? Or do we need to have a whole altogether new design at edge to solve these problems?
Okay, so there are a lot of innovations happening there where you do the only the lightweight
Right,
at
yeah,
edge and move the
correct.
remaining one to the data center.
Yeah.
But I'm not sure of what is the latest one that's been used on the edge side.
Especially with federated learning concept. So now the models are being pushed into where the data is, right? Like in our phone also there are models running, and all these models, whatever they have learned, they have to capture and then they need to synchronize. And Edge is evolving a lot in that space because a lot of companies' data coming across the CDNs, right? So at that space, so far it's just only doing the inference at edge, but now they are also going into the learning and fine tuning at edge. So when that thing comes, whatever the problems you mentioned, these challenges would definitely come across there. But since we have the flexibility at everything running at the origin server, so you may have much flexibility to put all these things at your origin server. But at edge, we don't have that much flexibility. Yeah. Anyways, yeah. Thank you.
So edge, I'm not so much following on that space. Like,
So Google is not doing much in the edge computing federated learning space.
they are doing, but my job is primarily on the Google data center, the main data center. So so our job is basically to provide infrastructure for cloud customers who are using GCP, like who are using GPU or TPU machines. So it's mostly for data center, not on the edge side. At least Google might be definitely doing, but I'm not following what is happening on that side. Okay. Okay. Mm-hmm. Okay.
So we have a question on the chat. What challenges remain in designing these networks?
What challenges? I think optimizing the tail latency, that is the biggest challenge. So with technologies like RDMA, and I think with technologies like RDMA, GPU direct, so these the tail latency is very much reduced. So the main challenge is optimizing tail latency. That is the reason why we cannot use standard TCP/IP, and then we move to things like SmartNIC and RDMA.
So is that the future direction?
I would say like any AI cluster should be using technologies like RDMA or GPU direct. If they are running on standard TCP/IP, then it's definitely not scalable. Yeah.
Okay. I think Daniel had his hand up. So Daniel, go ahead and ask your question. Oh, I think he dropped off. Okay, any other future directions you have? Any other future directions?
Future directions in
Like
this.
what is coming in this area?
Like obviously models are growing faster. So we have to make sure that the network, like even larger models are coming up. So we have to make sure that network can meet such uh, requirements of such model, such huge model training. So Google is always looking to make their network bigger and then scale. So I cannot talk more about those stuffs. Like whatever is there. Like I think if we can actually, I think cloud as a cloud customer, you can definitely try uh, some of the GCP products like A4 VMs. So there is a VM family called A4 VM. So that basically uses this rack optimized architecture that we described now. So users can use that A4 VM family and they can leverage this hyperscale networking. Yeah.
Yeah, so there's one more question on the chat. Can you share your views on Ultra Ethernet?
Ultra Ethernet Consortium. Yeah. So that is the upcoming one, like at Ultra Ethernet. So that's an upcoming technology. So I don't know much about that. Like it's still upcoming, and at least it's still upcoming, and I don't know much about that technology. Yeah.
Okay. So RDMA and even zero copy, they are not new, right?
Yeah, they are no. So they were once
decades old, right?
very much decades old, but they were mainly in the infinity band and high performance computing. They are not designed to run on commodity Ethernet. So they require a very specialized network of fabric, which is lossless. And they have been used only in high performance computing. So now with the AI and LLM training, we are bringing that concept to data center networks. Yeah.
Okay.
Yes.
Yeah, that's what. It's decades old.
Yeah, it's very much old. RDMA technology.
So the Redis also uses the zero copy. That concept itself is pretty old, and I think you guys are bringing that into the AI space, the GPU space.
Yeah. So
yeah,
I think it's a general
correct.
industry
It's
trend
general
in the
concept.
industry.
Yeah,
Trend.
yeah.
So from RDMA only things like GPU direct and all is evolved. Yeah.
How are you today? I'm Todd Besnick. I'm with Bitterly.
Mm.
So I think probably at Alphabet, the people that are doing the most type of edge things are probably the Waymo group and a couple others, not so much Google Cloud. So at the University of Wisconsin in 1995, we finished the cluster of workstations, which had a neighboring node fetch latency of 5 to 10 microseconds, which is basically the same as what I'm seeing here 30 years later. Do you have an opinion on that?
Can you?
We haven't changed in 30 years. We haven't found a better way. Something different. Cerebrus reports an across the wafer latency of 1 microsecond. That's 1 basis 10 better. So why are we doing it this way anymore?
So your question is why latency has not improved? Is that
No? So in Cerebrus, where we have 1 mic latency instead of 5 to 10, how much better would that be? Were you able to use the Cerebrus hardware?
I'm not familiar with the hardware that you're mentioning, but here with the SmartNIC and RDMA technology, it's not a small improvement in latency. It's a major improvement. Like from double-digit microseconds, we are going to sub-microsecond level,
Oh,
and then even like so. If you take a the slide had some, I think the slide had a one of the slides showed that like in a 10K GPU cluster, like when you connect them using regular standard TCP/IP network and versus you are using SmartNIC and GPU direct, like what is the model flop utilization? So that itself has a very good evidence that like the gain that we are getting is not just small number; it's a huge gain. Yeah.
hmm.
So obviously anything that is done by hardware, software cannot match. So here we are moving everything to the hardware. Like even the transport protocol, we are moving down to the hardware. It's completely burnt into the silicon. So obviously software cannot match the hardware speed.
Sure. So I would think that using ATM instead of TCP switching would be better.
ATM.
Asynchronous transfer
To-
mode.
Okay, but
We
data
worked on
center,
that in the late
but
80s.
data center is a commodity data center, right? Like we cannot design ATM fabric specific.
So you're using NVLink. That's not commodity.
NVLink is within a single server. It's not.
Yes.
It's
Well,
within a
ATM switches have been available since the 1980s.
Okay, so the goal is to be able to run this huge LLM trainings on commodity data center. So Google data center is not just runs AL training, like it runs other Google services as well.
Sure.
So it's a common shared network. Like you cannot build a specialized one. So what we are doing is optimizing and for that. Yeah.
Okay.
So, yeah.
So you mentioned the MFU, model flops utilization measurement.
Mhm.
Is that similar to the good put measurement as defined by Meta?
So in the AI world, they measure the performance by the floating point operations per second, like that's model flop utilization. So that measures like how efficient the GPUs are.
It's a utilization measurement.
Measurement,
the
yeah.
good
So
put measurement is also a utilization measurement. I was
measurement.
wondering if you thought they're basically the same.
You're talking about Meta, sorry?
Yes, they define this as good put.
Good put. Oh, okay, yeah, yes, exactly. It's the same, yes.
Oh,
It's
thank
the
you.
same, yeah.
Oh,
Yeah,
cool.
sure.
This is very cool. Thank you.
Oh, okay, yeah, thanks.
Thank you so much for the presentation. So that was quite insightful. I will quickly wrap up with a brief introduction to the chapter because this is supposed to be an open house and we have like 68 registrations. So I will quickly go over the slides that I prepared to generally go over the chapter activities and stuff like that. Uh, Okay, so yeah, my name is Vishnu Pendyala. I'm the chair of the chapter. Uh, we typically organize one event every month, and these events are mostly online, except for a few which are in person, like today's. There's supposed to be an open house, open to public, to generate interest and membership as well. So we have in-person events once or twice in a year. We have been having once or twice in a year, but otherwise most of the events are online and they are broadcasted live. Even today's event is being broadcasted live. And we were fortunate to feature distinguished visitors and international speakers from University College London, UK, IIT, and all the reputed institutions from all over the world. We started the Ask Me Anything series featuring distinguished lecturer Professor Alice Smith in November 25. We organize an annual symposium, ISCI. The first one was largely successful, and we are working on the this year's. And most of our events are typically co-hosted by other chapters from other sections. And we have a quarterly magazine, The Cognitive Nexus. Sometimes we summarize it as a podcast. So this is in the second year now. We have a website. We are hoping to keep it up to date. And then social media pages, please feel free to subscribe to them. We also have a meetup group. We have 1,000, more than 1,000 members. And the good news is that the membership grew by 30% in the first 10 months that we took over. So as you can see, in 2024, the membership was 140, and in 2025, these numbers are from October 25, when I pulled up the statistics. So we grew by 42 members. We are working on improving the diversity aspects of the membership as well. But right now, this is how the diversity numbers look like. And we have one or more events every month on topics like generative AI, agentic AI, large language models, ethical AI. And today we covered hardware as well. And we had a well-received talk on use of AI in cybersecurity last year. And we sometimes co-host other chapters events, just like they co-host our events. So the International Symposium on Computational Intelligence that I was talking about is available on the YouTube. So you can watch it. It was quite well received. And these are the kind of numbers of attendees for our events. As you can see, we had a lot of attendees for the agentic AI event. So that was the most popular event so far. And the other thing is, this is just the count of the live attendees, but we also have the content on YouTube, which is watched by several others offline. So all the, or at least most of the events that we had are available on YouTube, so you can watch them. So these are all the videos. And in terms of leadership, we have our treasurer, Venkat Gopi Kolla here. So I don't know if they can see you, or you can come here maybe. So Mayank, why don't you also come here? So Venkat, okay, let me do this. Yeah. So Venkat is our treasurer, and Mayank is our secretary. Our vice chair is Shravan Kanukolanu. He's not here today. And it's really that there's a lot of traffic these days, so it's understandable. And then we have a lot of other members supporting us. We have the past chair, Priscilla Chen, who is still active. She was a treasurer last year. We have nominations committee helping us with the elections. Dr. Sudhir Kshirsagar is the chair of the nominations committee, helped by Ken Doniger and Gauri Sarod. We have Rahul Raja and Arpit Vats helping with the editorial board of our magazine. And we are always looking for volunteers, provided they stay committed for at least 1 or 2 years. We require help with editorial support, social media, publicity, and student chapter. I'll talk about it in a second. Conference organization and all others. So, so let me do this. So yeah, so I think it is a great opportunity for students to start a student branch chapter. We already have a student branch in San Jose State University. So it's a good idea to start a student branch chapter as well. So that way they can participate in AI, machine learning, and data science workshops that expand their technical skills. And the good thing is for undergrad students, the membership is very affordable, just $24 IEEE membership. And I think it's $4 for the society membership. It's one of the most affordable societies, Computational Intelligence Society. So, and there are a lot of benefits. So students can, what is, oh, yeah, it's open access. Yeah, that's right. ACM has gone open access entirely. So they're charging the authors instead of the subscribers. Of course, they have a subscription. They have tie-ups with others. But that's probably a good direction. But yeah, we are talking about IEEE Computational Intelligence Society. So the students can gain a number of discounts and publications and resources. Collaborate with peers and mentors across universities and industries, take part in global challenges, hackathons, and competitions. So one of my students, undergrad students, participated in a competition, a computer society competition, and he won a trip to the IEEE Big Data Conference. Um, uh, it was all fully paid by the society. So things like that, opportunities like that are abundant. And then students can develop leadership, teamwork, and project management skills by organizing branch activities. Then there are plenty of awards, scholarships, and travel grants for students. Our own section has sometimes offers grants. And then the branches can get funding and support from various sources. So with that, so do you like to add anything, Mayank and Venkat?
Hey everyone, my name is Mayank Jindal. Happy to be part of IEEE CIS Silicon Valley chapter. I'm looking forward to contribute to this chapter and get involved in conferences and assist in event organizations and everything. Thanks.
Hi everyone, my name is Venkat, and thanks Dr. Vishnu for the opportunity. And I'm looking forward to contribute. And also, I see this as a great learning opportunity where I can meet a lot of people and also a lot of learning resources. So yeah, I'm looking forward for the chapter.
Okay, thank you. I don't see any questions on the chat window or in the room. So I guess we'll end the meeting here. Thank you all for joining, and hopefully see you in the next event as well. Bye now.